In this final section, section 3, we'll take a look at problems 4 and 5, of which you had to answer 1. By the way, as I say this, a number of you answered more than one problem in either or each of these two sections, 2 and 3. As you did that, I maybe didn't recognize that as I was going through them because I score them all a page at a time, and so I'm not necessarily looking at what you've answered before. I look at page 1 for everybody, and then page 2 for everybody, page 3 for everyone. And it's not until I go ahead and start to actually accumulate or tabulate the points that you've got that I notice that some people answered all the questions or answered both questions in one section, etc. That's not a good idea, by the way, because you're not only consuming your time budget, but you're also putting yourself in a situation where I may simply go ahead and score the first one I come to, whether that's the one that is best for you to have me score or not. So in this case, some of you answered both of them, but then didn't cross out one, telling me that that's not what you want to have scored. Now, I went ahead this time and scored each of them if you did 2 in any given section, and I went ahead and gave you the score for the one that had the greater point value, so the fewer mistakes. On the final exam, I won't do that. On the final exam, if you choose to answer more than one problem in a section that only requires one, I will score the first one I come to, whether it's the better performed one or not, and that's the one that you'll receive your points on. So just kind of take that and don't let yourself be put in a situation where you cause yourself a problem with this. So with that, let's look at number 4. So number 4, we're saying, suppose that initially the Utah economy is in equilibrium. So supply of labor equaling demand of labor, no unemployment. We're market clearing. With these following supply and demand relationships, we've got labor supply equaling 150,000 plus 250 W, and labor demand of 1,900,000 minus 220 W, where W is the monthly wage and L is the number of workers. So this is our initial condition. Now, a surge in high-tech development motivates workers to enter the state. So people in other states that are high-tech workers are hearing, hey, in Utah, there's no unemployment. You have this relatively good wage that's being paid as a market clearing wage. Maybe that's better. Let's move there. This is a classic mobility story, of course. So we find that 50,000 workers into the workforce at any wage level. That's going to become important to us in a few minutes. So that's our buildup. So the first question is, what are the equilibrium wage and labor in this market before the high-tech development? So also before then, the increase in workers. So we're simply going to equilibrate labor supply and labor demand. We've done this many times. I won't work through all the math on it, of course. You've seen this before. And we're going to end up with a W star of $3,723.40. So that's the monthly wage. It's not a huge monthly wage, but it's not a bad monthly wage either. And so that's the monthly wage, is W star, and L star, which is the number of workers in the state, is 1,080,851. There's some little remainder here. I don't know how we have a 0.06 of a person, but we essentially then have 1,080,851 workers, each being paid $3,723.40 per month. Not bad. And those are the values that you should be looking for. And obviously, when we look at this wage number, it's 1,750,000 divided by 470. That's going to equal to 3723.40. It was interesting. I saw that a number of our international students simply tried to use this equation as your final value, and I would not have necessarily appreciated that, but I also wouldn't have given you a big deduction for it. But when they used that value as a fraction and plugged it in elsewhere, those students had some difficulty with some math problems because it's just a cumbersome value. this is a much simpler and easier to use value. 3,723.4 is just much easier to use in other equations than 1,750,000 divided by 470. Okay. So then in part B, I say, what is the new labor supply equation given the influx of workers? Well, we had an initial labor supply of 150,000 plus 250W, and we're simply going to add 50,000 workers to it. I gave you an example exactly like this in one of our video segments when we talked about labor supply, and then again when we talked about mobility. So this then becomes 200,000 plus 250W. And most of you pegged that. I was actually pretty pleased with that. And then I ask, what are the market clearing levels of wage and labor following the influx of workers? Well, once again, we're now just going to equilibrate. But we're going to equilibrate the new labor supply against the existing labor demand, because we have no indication that labor demand has changed. So it's a bigger labor supply, so we would expect it to give us a slightly lower wage and a greater number of workers. And in fact, that's exactly what it did. We now end up at $3,617.02 for W prime, the new equilibrium. I use prime instead of star simply to differentiate here. And then L prime of 1,104,255 workers. Okay, that's all fairly straightforward. Now we go ahead in the last part of this and I say, give me a fully labeled labor market model representing both the original condition of this market and the market following the high-tech development. I want it all done on one graph, which everyone did, and I just indicate I want it all relevant values, appropriately labeled, and I suggest that you think about scales and intercepts. Well, you did fairly well on this, most of you, and correctly identified that our intercept values on the labor demand relation on the labor axis, the x-axis, is 1,900,000, because that's what we get. Let's remember what our labor demand curve is. 1,900,000 minus 220W. So labor demand, 1,900,000 minus 220W. So if W is 0, which it is on this axis, what is labor demand? Well, it's 1,900,000. And then we saw further that that same labor demand curve had a wage or y-axis intercept of 8,636.36. Well, we get that by saying that labor demand is 0. So we then have 220W equals 1,900,000. And then that tells us that W is 8,636.36, and this is that intercept on that axis. We can then each easily think about the supply curves, which were 150,000 plus 250W. Let me change pen colors for a moment. So labor supply at 150,000 plus 250W. And we had labor supply prime, let's say, at 200,000 plus 250W. And we identify the intercept values on the labor or x-axis, as we know that we've set W equal to 0, which means 250 times 0 is 0. We are at W equals 0 any place on this. And so labor supply is 150,000 and labor supply is 200,000 as the intercepts. So we can then go ahead and plot those, and we already know what our W stars and our L stars are from the prior parts of this. So we should have the intercept values, all four of them. We should have W star at 3723.4 and L star at 1,080,851. We should have W prime or W something that differentiates it from W star of 3,617.02, and then L prime of 1,104,255. Something I saw in this that was a little bit concerning to me for a few of you was that you gave me the right labor demand curve. Oh, you may or may not have labeled it. And you gave me a labor supply curve. And once again, you may or may not have labeled it. But you did give some W star and L star. And then when you provided another curve representing the additional workers, gave me, in some cases, a downward sloping curve that looked for all the world like a labor demand curve, even though you may have given me the right modified labor supply equation. So I was kind of confused at that. It simply told me that you perhaps don't understand the dynamics of that equation, of that curve. And if you had that problem, I would ask you to go back to the first couple of modules where we talk about the formation of those curves, evaluating labor market models, because you're probably having some other difficulties that will cost you yet again on the final exam. Okay, so let's finally now move into problem number 5. Problem number 5 is an elasticity problem. I talk a little bit about labor unions here, but you didn't need to know anything about labor unions to figure this out. And so, or at least I talk about differentiated markets that might be thought of as union markets. So we're going to look at this then and say, okay, we've got two different types of workers in a given market. One type is low skilled with low wage. The other type is highly skilled with a high wage. We'll call these workers high and low. Minimum wage in the market is $7.25, which, by the way, turned out to be irrelevant. L is equal to the number of workers in hundreds. And L has a labor demand schedule of LD of L of 20 minus 2W of L. And I has a labor demand of LD of H equals 20 minus W of H. So relatively similar. Low is equal to 20 minus 2W. High is equal to 20 minus W. And labor supply is the same for both firms. Okay. So I say go ahead and identify the own wage elasticity for workers at each firm based upon a proposed wage increase of 10% using the simple elasticity formula, and specify the type of elasticity for each worker. So all I've done here is I've set up classically my L1, L2, W1, and W2. So I know what the W1 is. W1 is the equilibration value of wage when I've set labor demand and labor supply equal to one another. So I do that, and I find that W1 is 7.67. And I find that L1 is 4.67. And that's just the that's just the W star, or in this case I call it W1 and W2. It's just W star arising from the equilibration of labor supply and labor demand for low. Well, I now know that I need to change the wage by an increase of 10%. So I go from 7.67 to 8.44, which is 110% of 7.67. So I added 10% on top of 7.67 to get to 8.44, and then I use that value of wage, plug it into the labor demand equation, not the labor supply equation, the labor demand equation, because we're looking at the own wage elasticity for workers. This is a demand issue. And so I've gone ahead then and had it plugged into the labor demand equation, and it tells me that my L2 is 3.12. So now in classic form, I essentially say L2 minus L1 divided by L1, and all of that divided by W2 minus W1 divided by W1. Labor in the numerator, wage in the denominator, in the simple form. And as we've done that, we then can work through, see, 3.12 minus 4.67 divided by 4.67. That's going to be the same as negative 1.55 divided by 4.67. And then we can look at 8.44 divided by 7.67, all of that divided by 7.67, which is the same as 0.77 divided by 7.67. In some cases, you're tempted now to take each of these terms, the numerator term and the denominator term, and convert them to a decimal rather than keep them as fractions. I would encourage you not to do that, because when you do that, you almost always will round to some decimal. 1 decimal point, 2 decimal points, 3 decimal points. And when we do that, we lose a little bit of clarity. We lose a little bit of detail or fidelity, if you will. So I always keep them as fractions here. And then, because it's easier for me to deal with fractions as a product or multiplying them, I go ahead and invert the denominator and then multiply these two terms together. And I'm going to end up then with negative 3.30 as the elasticity, and I know that that is elastic. Negative 3.30, its absolute value is greater than 1, it is elastic. So that's low. I've done the exact same thing for high, only I've used the high labor demand equation rather than the low labor demand equation. I equilibrate high's labor demand of 20 minus W with labor supply, same for both markers of W minus 3. That gives me a wage, which is W1 of 11.5 and a labor of 8.5. And I then go ahead and increase 11.5 by 10%. So 11.5 times 1.1, and that yielded me W2 of 12.65. And then with that new wage, I plug that into the labor demand equation, and I come with a new L, or L2, of 7.35. And then I've gone ahead and used the simple formula again to come up with my values, and you can walk through this here. 7.35 minus 8.5 divided by 8.5. All of that divided by 12.65 minus 11.5 divided by 11.5. That's going to yield us a value that is negative 1.15 divided by 8.5 over 1.15 divided by 11.5. It's coincidental, by the way, that these 1.15s in their respective numerator positions are essentially the same number, just coincidental. I then go ahead and invert the denominator so I can multiply rather than divide, and I've got negative 1.15 times 11.5 is equal to 13.23, and then 8.5 times 1.15 is 9.78, and I now take this fraction and I divide this so that I get a negative 1.35, which the absolute value of negative 1.35 is 1.35 greater than 1. It is also elastic, but it's not as elastic as the first value. So the high workers are relatively inelastic compared to the low workers, which shouldn't surprise us in the least. The low workers have a lower wage. We know the lower wage means lesser skilled. We know the lesser skilled means more substitutable. More substitutable means more elastic. Okay, so that's A. A lot of little calculations in there, but nothing very difficult. Now we go and look at B. I said, okay, what would you expect to happen to a total wage bill, or all of the wages, in a firm employing these two types of workers in the event of the wage increase? So based upon this elasticity. Well, and I ask you to provide a separate answer for each type of worker. Well, you can do one of two things here, and regardless of which one you did, you probably should have fact-checked it or double-checked it against a kind of a natural check that you should know from reviewing the modules on elasticity. First, we know that when something is elastic, when the wage goes up, the total wage bill goes down. That's simply a function of the fact that we'll lose more workers proportionally than we had in wage increase. So the total wage bill is going to go down. And so you might have memorized that. When it's elastic, the wage and the total wage bill work inversely. When it's inelastic, they work in the same direction. Well, we can check this. I know the number of workers and I know the wage. So if I look at this and say, okay, W1, my initial level of wage times my initial level of workers was 7.67 times 4.67, or 38.82. All right. Well, how does that compare to the new wage and the new level of workers? W2 times L2. Well, 8.44 times 3.12 is 26.33. Okay, the wage went up and the total wage bill went down. Check. I now do the exact same thing for high, which I should see the same result, although maybe in slightly different proportions because it was also elastic. So W1 times L1, 11.5 times 8.5, that's 97.75. All right. The higher level of wage, so W2 times L2, 12.65 times 7.35, that's 92.98. It's not much of a decrease, not nearly the proportional decrease we saw here for the low workers, but it similarly is a situation in which the wage went up and the total cost of labor went down. The wage bill went down. Check. It's exactly what we expected. But notice the dynamic difference. These are different in similar proportion to the difference in these elasticities. Negative 3.3 for low, negative 1.35 for high. All right. Then in part C, I say, suppose that the wage increase for low resulted in a cross-wage elasticity with a negative value. So remember, cross-wage elasticity is going to be L of worker I, L of worker I, labor of worker I, with, or percent change, percent change in labor for worker I divided by percent change in wage for worker J. And I and J are simply suggesting they're different types of workers. So if this is going to result in a negative value, what do I think I'm looking at here? Well, this is going to be an issue of substitutes or complements because it's cross-wage elasticity. Workers either are substitutes of each other or they are complements of each other in cross-wage elasticity. So if it's going to be negative, if this is less than 0, then what does that mean to us? Well, let's think about it. When the wage of worker J rises, that should, given that we're talking about demand, yield a decrease in the number of labor units for worker J. Well, in order then for this term that we're going to end up with to still be negative, because we've got a positive and a negative, so we've got a negative term so far, we better keep it that way. So we then need to think of this as labor for worker I must also be going down, because it's this and this that we're comparing. Labor I, worker J. Labor I, worker J. Well, if worker J, if the wage went up, then we must have the number of labor units for I going down to get this negative value. If that's the case, then the labor unit change went in the same direction for the worker we're looking at the wages of and that we're looking at the labor units of. These must be complements. If we don't need one of them, we don't need the other one. Or if we need more of one, we need more of the other as well. They're complements. So this turned out to be complements. We can think about substitutes in exactly the same fashion. So if worker J, if the wage goes up, we know still that the labor for worker J is going to go down. Well, if we're measuring these two values, I and J, not J and J, but I and J, then in order for this to be a positive term, we must have the labor for worker I going up. Well, if one goes down and the demand for workers in general has remained constant, then that means the demand for the other has gone up if they are substitutes. And we actually went through an example of this a couple of times in the modules on this. Finally, we go ahead and I say, okay, do the elasticity values you calculated in Part A, do these change if we use the midpoint formula? And recall that the midpoint formula is L2 minus L1 divided by L2 plus L1 divided by 2, and all of that divided by W2 minus W1 divided by W2 plus W1 divided by 2. So we're using the exact same L1, L2, W1. W2 we used in the prior section on this and in Part A, and we're just exposing them to the midpoint formula now. And not surprisingly, we see that there are some changes. In fact, we see that instead of 3.3, which was what we saw initially, negative 3.3 for low, we see that low now is negative 4.16. So it's even more elastic than we thought it was. Similarly, we had looked at a negative 1.35 for high workers, and that's still elastic, but we find they're even more elastic than we thought they were when we employ this midpoint formula. Well, why are these numbers changing? Because we have a relatively significant change in wage. We have a 10% change in wage, which if you're earning minimum wage, that's not a lot of money. That's $72.5 per hour. But 10% change in anything is a relatively large change in anything. And remember that you were instructed that when we have a large change in wage, that the simple elasticity formula will not be nearly as accurate as the midpoint formula. And so the midpoint formula will tell you with greater accuracy, greater fidelity, what our elasticities are. And in this case, they were more elastic than we thought they were. That's not necessarily the case. They may have been less elastic, or one might have been more and the other less, depending upon those demand relationships. We don't really have any change in the type of elasticity, just the significance or the fidelity of the elasticity here. So this is then question number 5 in its entirety. Not very many of you chose this one, although I thought that this one was one of the simpler ones in terms of concept, although perhaps maybe more difficult in terms of the slight or the number of calculations that you had to perform.